Hello, good morning. Today we're going to talk about magnets. A magnet is a very special metal. When a magnet goes near a special kind of metal or other magnets, and the poles touching are opposite, it will pull or attract the other metal or magnetic closer. Also, if the two poles are the same, the two magnets will push away or repel. But if the two poles are different from each other, it will attract. This is called magnetism. Did you know that there are three types of magnets? First, the temporary magnets. Second, the permanent magnets. And third, the electromagnets. Temporary magnets. Temporary magnets are those that simply act like permanent magnets when they are within a strong magnetic field. Unlike permanent magnets, however, they lose their magnetism when the field disappears. Paper clips, iron nails, and other similar items are examples of temporary magnets. Temporary magnets are used in telephones and electric motors, amongst other things. Some iron and iron alloys can be easily magnetized by even a weak magnetic field. However, when the magnetic field is removed, the object gradually loses its magnetism. Second, permanent magnets. A permanent magnet or ferromagnet is a material that produces a magnetic field. Permanent magnets are made from ferromagnetic materials such as iron and are created when the material is placed inside of a magnetic field. When the magnetic field is removed, the object remains magnetized. Permanent magnets have a permanent magnetic field and do not turn on and off like electromagnets do. Permanent magnets are the oldest type and still used for a wide variety of applications today. This is how permanent magnets work. Permanent magnetization of a material involves its electrons and how they move around their nucleus. In most materials, electrons move in a rather spontaneous manner. In a ferromagnetic material, however, electrons align themselves and spin in the same direction while orbiting their nucleus. This produces a small magnetic field. As more electrons align themselves, the magnetic field becomes stronger. In this case of permanent magnets, electrons tend to stay aligned un unless heated above the Curie temperature and then cooled. Examples: a horseshoe magnet made of alnico, an iron alloy. The magnet made in the shape of horseshoe has the two magnetic poles close together. Third, electromagnets. An electromagnet is a magnet that is created using electric current created by electricity. Since electricity can turn on and off, so can an electromagnet. It can even be weakened or strengthened by decreasing or increasing the current. These are used when a very strong magnet is necessary. Electromagnets are made by placing a metal core inside a coil of wire that is carrying an electrical current. The electricity going through the wire produces a magnetic field. While the electric current is flowing, the core acts as a strong magnet. Computers, TVs, and electric motors use electromagnets.
Hello everyone! Today we're gonna tackle about what is a magnetic field. A magnetic field is a picture that we use as a tool to describe how the magnetic force is distributed in the space around and within something magnetic. When we speak of the force due to a magnet, or any force for that matter, it has to be on something. Strictly speaking, a force vector field tells us the magnitude and direction of a force on a small test particle at any point. Most of us have some familiarity with everyday magnetic objects and recognize that there can be forces between them. We understand that magnets have two poles and have, depending on the orientation of two magnets, there can be attraction, opposite poles, or repulsion, similar poles. We can recognize that there is something region extending around a magnet where this happens. The magnetic field describes this region. There are two different ways that a magnetic field is typically illustrated. The magnetic field is described mathematically as vector field. This vector field can be plotted directly as a set of many vectors drawn on the grid. Each vector points in the direction that a compass will point and has length dependent on the strength of the magnetic force. Arranging many small compasses in grid pattern and placing the grid in a magnetic field illustrates this technique. The only difference here is that a compass doesn't indicate the strength of a field. The second one is an alternative way to represent the information contained within a vector field is with the use of field lines. Here we dispense the grid pattern and connect the vectors with smooth lines. We can draw as many lines as we can. The field line description has some useful properties. Magnetic field lines has never crossed. Magnetic field lines naturally bunch together in regions where the magnetic field is the strongest. This means that the density of field lines indicates the strength of the field. Magnetic fields don't start up or stop anywhere. They always make closed loops and will continue inside a magnetic material, though sometimes they are not drawn this way. Field lines can be visualized easily in the real world. This is commonly done with iron fillings dropped on a surface near something magnetic. Each filling behaves like a tiny magnet with a north and south pole. The fillings naturally separate from each other because similar poles repel each other. The result is a pattern that resembles field lines. While general pattern will always be the same, the exact position and density of lines filling depends on how the fillings happen to fall, their size and magnetic properties. That's all and thank you.
Hello everyone, today I'm going to show you how magnetic field lines work. Magnetic field lines are not visible in our naked eye, so this is the representation of magnetic field lines. Magnetic field lines works through the distance of the magnet. As you are closer to the magnet, the denser the lines, the stronger the magnetism is. And when the further to the magnet, the lesser the line is, the weaker the magnetism is. So that's all. Thank you.
Okay, so now we are going to talk about magnetic poles. There are different ways of defining magnetic poles. The most common understanding is that they are the positions on the Earth's surface where the geomagnetic field is vertical. These poles are called dipoles, and the north and south dipoles do not have to be, and are not now, antipodal. In principle, the dipoles can be found by experiment, conducting a magnetic survey to determine where the field is vertical. Another definition comes from the global models of the geomagnetic field. Models of this type, such as the International Geomagnetic Reference Field, or the IGRF, include an equivalent but fictional magnetic dipole at the center of the Earth in their representation of the field. This dipole defines an axis that intersects the Earth's surface at two antipodal points. These points are called geomagnetic poles. The axis of the equivalent pole is currently inclined at about 10 degrees to the Earth's rotation axis. The IGRF can also be used to compute dipole positions. This model, dipoles do not agree with the measured dipole positions. The geomagnetic poles and model dipoles cannot be located by direct local measurement. The locations of the model dip and geomagnetic poles are shown in figures 1 and 2. And that's it. Thank you for listening to me discussing the magnetic poles.